Hi, this is Jalani Williams from CMU, here to talk about some joint work that I did with my advisor, Weina Wang, and Professor Anupam Gupta. That'll be appearing in ITCS 2022. We call it probing to minimize. And so the first thing you might be asking is, what is probing? And to kind of help elucidate that, I'm going to talk about like a few specific examples of probing. The most basic concept that defines probing is that there's some randomness in the world that you have to interact with in order to find out what its value is. So the first example we're going to do is home renovations, right? When you're trying to get your home renovated, you have to call up contractors, but you don't have an infinite amount of time to call up these contractors, right? So when you call them, you have to be judicious about who you're calling. And say you're trying to like minimize the final cost you end up paying. Well, when you're calling off these contractors, you have to make some decisions about who you're calling if you want to minimize that final quote. The second example we'll go with is vaccine research funding. If you're a government who's trying to get out a vaccine as soon as possible, then you need to decide how to distribute your funding in a way that accomplishes that, right? Some scientists might put forth proposals for sort of riskier options when it comes to like vaccine research, right? And some might go for sort of more tried and true methods. And by getting the right balance of them, you can minimize the amount of time it takes for you to get a viable vaccine. And the third example we'll do is a record collector. Say you want to get the most pristine version of a vinyl record, of a specific vinyl record as possible. And so you'll run around all of these record stores, but they don't let you actually see the condition of the record until you buy it. Right? There's a trade-off you'll need to make in where you're buying records from, right? You could just go to like your standard record store and like find a perfectly decent record at probably a pretty decent price as well. Or you could go to, more eccentric record stores and maybe find some hidden gems that are preserved in like pristine condition, right? So you need to somehow balance this ability to explore and this ability to take risks with actually minimizing your final objectives. Okay. So now let's talk about the formal model. So in the formal model, there's a universe U of elements, which we just refer to by numbers from 1 to n. For each element in that universe, we associate a random non-negative integer, which we call its weight. And we're going to be building sets in these problems. So we also have a collection of the feasible sets, which we write as script f. And we have an objective function f, which takes as input all of the weights of our selection set. But we write that as f of s sort of like as an understood convention that when you write f of s, really like behind the scenes, the weights are having an impact on the objective function. And with all of that set up, our goal is to minimize the expected objective value, final objective value of our selection set. An important distinction we have to make here also is adaptive versus non-adaptive, is the adaptive versus non-adaptive setting here. In the adaptive setting, you're building your selection set, one element by element. And once you select an element and add it to your set, you get to see its random weight and adapt your strategy based on what you've seen so far. Whereas in the non-adaptive setting, you don't get to see anything until the end. So you're essentially choosing all at once. Okay, so with this formal model, what is known? Well, for maximization, actually, like there are a lot of results for adaptive maximization probing problems, right? There's this huge bountiful forest of results based on contingent resolution schemes, profit inequalities, LPs, submodularity, greedy algorithms, everything under the sun. So what about minimization? Minimization is more like a desert. There's really not that much known about minimization probing problems, not even for the sort of most basic function that you can think of, just the minimum weight element in your selection set. Okay, so what is known actually for this minimum element objective function? And we sort of wrote the problem statement here on the left, and we're going to look specifically at the case where there's a knapsack constraint for our set, right? Most of what we know is from How to Probe for an Extreme Value, a paper by Goel, Guha, and Munagala from 2010. And they give some really nice results for the non-adaptive problem, specifically in the case where the random variables are integers from 0 to m. Right? They show a few things. The first thing they show is that it's actually NP hard to approximate this problem without relaxing your budget. So you sort of have to relax your budget to get anywhere. And once you relax that budget, they also give like a by criteria approximation scheme that sort of includes this log m factor that you'll see here, right? And they do that using, you know, submodularity and a greedy algorithm plus like an LP to get like a good initial condition. And at the end of that paper, they sort of left obtaining adaptive approximations as a challenging open problem. So what about this problem actually is so challenging? You know, why is it a desert? Well, one possible reason is that there's an asymmetry in what we're asking for when we ask for approximation algorithms for maximization versus minimization. And so as a good example, let's look at, you know, taking a test. Let's say this test is out of 100 points, and assume like the optimal you can get in expectation is 99 points, right? The smartest kid in the class is getting 99. Okay, so if you get a two approximation in the maximization context, that's saying your expected score is better than like about a 50%, right? Whereas in the minimization context, getting a two approximation means that your expected number of points lost is less than or equal to 2, meaning your expected score is like greater than or equal to a 98%. And so in certain contexts, it seems as though like when you ask for when you ask for an approximation algorithm in the minimization context, it's a bigger deal than in the maximization problem context. In a way, we're sort of, when we talk about approximate minimization, we're talking about like near optimal maximization. Okay, so that's all well and good, but maybe we can still use things from maximization to solve our minimization problems. And so one common route that people use to do this is, you know, they come up with an algorithm. They want to show that it's close to the adaptive optimum. And so the route they go through is to show first that their algorithm is close to the non-adaptive, their algorithm's like expected value is close to the non-adaptive optimal value. right? And they do that using conventional approximation techniques. And then the second step is to show that actually the non-adaptive optimum and the adaptive optimum aren't that far apart. They show that the adaptivity gap, or the ratio between optima, is small. Okay, and so, maybe one would hope that we can do this in the minimization context. Okay, so our hope is that, we have some algorithm, say specifically for the min element problem, and we show that it, and Goel, Gua, and Monogala have already shown that their algorithm is close to the non-adaptive optimum. So if we can just show that the non-adaptive optimum is close to the adaptive optimum, then we'll have adaptive approximations, and everyone can clap and then go home. But the reality is actually the route doesn't look anything like this. We give an example that shows that in general, the non-adaptive optimum can be arbitrarily worse than the adaptive optimum. We give an example where the adaptivity gap is arbitrarily large. Adaptivity gives you an arbitrary amount of power, which we won't describe that example now, but if you're interested, you can check it out in the paper. So now let's talk about what we were able to do in our paper. So for the MinElement objective function with a knapsack constraint, where one should recall that the MinElement objective function is just, f of s is the min weight element. It's the weight of the min weight element in f. For that setting, we give it adaptive approximation, the first adaptive approximation, with our expected objective value being less than or equal to 4 times the optimal, and our cost being log m times the budget, right? And this closes an open problem left by Goel, Guha, and Monogala in how to probe for an extreme value. So once we've done this, we also look at a generalization, which we call Mink-Knapsack, where instead of just looking at the min weight in S, we look at the sum of the smallest k weights in S, right? And there we also get an adaptive approximation with a slightly worse expected value, right? And with log squared k in the in sort of this resource augmentation factor on this cost factor, right? We also, in the paper, in the archive version at least, we deal with 2 other matroid-based variants. Okay, and so how did we do this? Well, the root behind all of our results is this new approach / meta algorithm that's based on adaptive probability minimization. And I know what you're probably saying right now is probability minimization, that sounds harder than expectation minimization. And in some cases, you're probably right, but in some cases it's actually tractable. So let me give you first some intuition about what we're going to do, or why we would even think this would work in the first place. So we start from just this expectation formula as the sum of these tail probabilities. So if you take a single term, for example, if you have this min element objective function with your knapsack constraint, and you look at t equals to 2, right? That's minimizing that term is a problem in and of itself. In particular, we call that a threshold problem because we're trying to get our objective function lower than some threshold. We're trying to say it differently, we're trying to minimize the probability that our final objective value is above some threshold subject to our constraints. So this is sort of an odd problem, and it's not obvious how you actually approximate these threshold problems, but that's what our key idea is actually. if you focus on getting adaptive approximations to these threshold problems, then, somewhat surprisingly, you'll be able to get some results. So let's go through an example of a threshold problem. And in this threshold problem, it's nice to describe things as sort of coin flips. And let me first explain what I mean by that. So you have this objective function, which is the probability that the min of all the elements you choose is greater than 2. So this is equivalent to saying that with every element, E, you identify each element with a coin. And it's a coin that's heads if if the weight of that element is less than or equal to 2, and it's tails if you're above 2, right? So then, in that language, our objective function is just minimizing the probability that we get all tails when we're going through and flipping coins, right? Okay. And so one thing you might realize, actually, is that this problem, even though we've cast it in an adaptive light, even though we're looking for an adaptive approximation, is essentially a non-adaptive problem, right? Because as soon as you get a single heads, well, your run is over, the game is over, you've won. And if you don't have a heads yet, well, it's as if you never flipped anything, but you sort of lost some budget and you lost some available elements to choose from, right? And so this tells us actually that like adaptivity gap for this problem is 1, which means we can reduce it to a knapsack instance, just through some slight manipulation. And that tells us that actually a greedy algorithm is a 1-2 approximation. It gets like a perfect, it gets like the perfect probability, but it uses maybe twice the budget. Okay, so just rest assured it is possible to solve these threshold problems, particularly in the min element case. It's a very nice threshold problem. Okay, and so now let's look at like realizing this basic idea we had before. So we have these probability minimization problems. We have a policy that we can run to accomplish this minimization, right? How do we turn that into a policy that minimizes an expectation? So just go back to this expectation as a sum of tail probabilities, and we'll define pi sub t as the policy that we're using to approximate this threshold problem, and S of t as its resultant set. So just the most basic, most naive idea that one could do is just say, okay, let's just run all of these pi sub t's and combine all of the S of t's, and that's going to be definitely better than the expected optimum. The only bad thing about this is that you also end up probing, like, you end up running like m of these things, where m is like possibly gigantic. So what we want to do is like maybe get that cost factor smaller, even if it results in like a worse like value approximation. Okay. Right. And so how do we do this? How do we go beyond this basic idea? Well, there are two like kind of clear problems with our approach right now. The first clear problem is that the thresholds that we're probing are kind of redundant. And let me explain what I mean by that. Because the summons in like this tail sum are monotone decreasing, we don't actually need to focus on minimizing every single term, because probably the policies are going to be very similar, and like these improbabilities are going to be like very similar in value. So long as we're able to capture the general trend, then we'll be able to approximate things well. And so what's our solution for this? It's just to round up to the nearest power of 2. If you do that, then the expected value of opt, or the expected value of any random variable, is bounded from above by the sum, which only includes like log m probability terms, and which is then again bounded from above by 2 times the original expectation. So that means that if we just focus on minimizing these log m terms, then somehow we'll be good to go while avoiding like a lot of the mess that we had before, right? And so if we just use this idea directly, then this gives us a cost factor of log of m, and gives us a value factor of 2, which is worse than the one we had before, but only by a factor of 2. So it should still be fine. The other issue with our basic idea is that we're not being adaptive at all, even though we have access to adaptivity. So for example, if we're just probing things in a certain order and we probe and we perform the threshold test at a threshold t before we do t plus 1, if we succeed at this threshold test, if we get an objective value that's smaller than t, we're still going to go try to do all of these threshold problems we're trying to get like an objective value that's larger than t. We're trying to get it below a threshold that's larger than t. So why would we ever do that? So clearly we need a smarter way to choose which thresholds to try. And what's the solution here? It's more involved. I'm gonna need like a few slides to explain it. But the basic gist is that we're going to search for the next threshold to try. Okay. Right. So the solution is adaptive binary search. And sort of the key idea here is to take advantage of the fact that you've gotten below a threshold if you ever do. So let me just walk you through the algorithm first, and then I'll sort of go through an animation that shows how it would work. So we're going to define a threshold test as you're at a threshold and you execute whatever approximate policy we have to minimize the probability, that tail probability that we were looking at before, right? And we define a success if we actually obtain an objective value that's lower than that target threshold, right? So our algorithm is this. First, you perform a threshold test at the median, and if you succeed, then you recurse with all the smaller thresholds, and if you fail, you just recurse with the larger thresholds. Okay, so let's see that in action. The median here is 2 to the 4, so we're going to perform a threshold test there. We set back, and we see that the objective value is actually less than or equal to 2 to the 4, is less than or equal to 16. And so we're going to recurse on the left. All right, so this is now this brown orange region is the available thresholds that we're looking at. Okay, so now we'll do this again. The median here is 2 to the 2 or 4, right? We perform this threshold test. We fail it, so we move to the right, and this sort of continues until you end up with nowhere left to go, no thresholds left to test, and at that point the algorithm terminates. Okay, so how do you prove that something like this works? Well, the key idea is to just analyze things based on an upper bound, and that's to analyze based on the highest threshold that you failed to test at. Even though it's technically possible for you to get an objective value that's smaller than the highest threshold you failed at, just through happenstance, by analyzing it this way, you can actually get a nice bound on what's happening. Okay, so that's the meta algorithm, and that's sort of that's the root, that's the core of of our paper here. So now let's look at the generalization, Mink-Knapsack. And there are a lot of interesting ideas here, and we won't have time to get into all of them, but I invite you to read the paper if like any of this sounds interesting. So the gist is that it's actually possible to do something similar in this generalization. In terms of, you know, solving this threshold problem. There's a complicated reduction process actually, but what it leads you to is is a generalization of this previous coin problem we looked at. Before, we had some constraints and we wanted to essentially maximize the probability that we got at least one head while we were flipping coins. Now, what we want is to get at least j heads. So when j equals 1, you'll remember the solution, the problem setting, is essentially non-adaptive. But when j is not equal to 1, this is not true in general. So don't be deceived. You actually need to use adaptivity to solve this. You likely need adaptivity to solve this. So how do we go about solving this? Our main idea is to reuse this greedy strat that we used when j is equal to 1, but now with an augmented budget. Now instead of just the normal budget, we also give it like enough money to buy like j extra elements. So along with this main idea, you have to reduce this like general case where items can cost like any amount from 1 to b, to a case where the cost is actually restricted to being like b over j. But that's actually not too tricky. With the simple binning technique, you can get that. Okay, so let me just talk about the Mink-Knapsack, the proof we have for like how to handle this threshold problem, or why this this extended greedy algorithm works. So what we do is make an inductive argument. We argue by induction. In this specific case, we'll look at j is equal to 2. So we want to get 2 heads at least. So in that case, the optimal decision tree, or really any decision tree, like modulo, like just modulo things that don't affect the final, their success probability at this problem, their decision tree is going to look like this. They're going to choose like a first coin to flip. If it comes up heads, then they're going to go to the right and go to like some subtree. If it comes up tails, then they'll go down to another element, element 2. They're going to flip the coin associated with element 2. And then if it comes up heads, they're going to go down to this tree 2, and so on and so forth. And the key thing to realize when you're analyzing this, when you're trying to prove that extended greedy is good in this context, is that in each of these subtrees, it basically looks like we're doing a problem. Like if you look at the system state, when you first move into that subtree, it looks like you're just starting a j equals 1 problem. And sort of the rationale for that is that like you're flipping coins and you need 2 coins. As soon as you get one, or you're flipping coins, you need 2 heads. As soon as you get 1 heads, it's like you're in this, it's like you now only need 1 more heads. You've gotten rid of some budget, you've gotten rid of some elements that you can choose from, but everything is essentially turned into like a j equals 1 case, right? And since we know that greedy works in the j equals 1 case, we sort of know that like once we landed those subtrees, that we'll be good to go as long as we're following the greedy algorithm, right? And so once we've shown that, like our main goal is just to, so now that we've shown that, we know that like the main thing that determines whether a policy is good is like how quickly it gets its first heads, right? And actually, the greedy algorithm optimizes for this. Like if you choose according to the heuristic that we've shown. And specifically, if we give greedy in like a little bit of extra budget to get a head start versus every other policy, then that's enough to show that it actually in some way like stochastically dominates all other feasible policies, which I think is a pretty cool result. Okay. And so that's, I think, all of the time we have for like technical stuff today. So just as a conclusion, first let me recap stuff. In the beginning, there's not much known for minimization probing problems, but in this work, we give a new approach based on what we call threshold problems, which are adaptive probability minimization problems. We also give bi-criteria approximations for a few threshold problems, which end up, when combining with this new approach, they close an open problem of Goel, Gua, and Munagala from how to probe for an extreme value, right? Open problems from this work are adaptive hardness. In how to probe for an extreme value, they showed that this non-adaptive version of the problem is NP hard to approximate without relaxing the budget, but essentially nothing is known about the adaptive case, and it's not even clear like how to start things off, given like how different adaptive optimization is to non-adaptive optimization. Another open problem is, in our like cost factor, there's like a log m there, and there's also a log m in the how to probe for an extreme value cost factor. And so one question is like, is that log m actually like fundamental? Like, is it possible to get lower than that, or is there something? Is there some core aspect of the problem that limits us to log m? And another natural open problem is it possible to get like an approximation scheme here instead of just these, these fixed factor approximation results that we derive in our paper? Okay, and so just some takeaways of the talk in the paper is that actually the greedy algorithm can have much stronger properties than you initially make use of when you like set up your heuristic. Like, I think there are a lot of aspects of greedy algorithms that we sort of take for granted that we don't always use to their fullest extent. And this is an example of if you do use those properties just like a little bit more, then you can actually get some very, very strong results. And then besides that, just iterative goal setting works. And that's kind of what our meta algorithm does. It does some iterative goal setting. And so that's useful in a personal context as well as an algorithmic context. Okay, so this is the final thing. Thanks for listening. If you enjoyed the talk or you're interested in anything here, feel free to email me and check out the paper on arXiv and also published in this current proceedings of ITCS. And thanks for all of the funding sources we have, NSF, the GEM Fellowship, and the Gates Millennium Scholars Program. Thanks for listening, everyone. And I'll see you at the conference.